So I was in Fusion EP like 3 years ago. I first year I was in Nancy, and second year I went to Belgium. Um, then I also in that year when I was in Belgium, I did my master thesis in Princeton Plasma Physics Laboratory for like half a year, and then at the end of this program, Fusion EP, I mean, I applied a PhD in MIT, also in other graduate schools, and then I got MIT afterwards. And then I came here. And the first 2 years I was working with Professor Ian Hutchinson, um, who wrote a book, Principles of Plasma Diagnostics, if you are familiar with that. Then because of some funding issue right now, I'm switched to another group. I'm working with Professor Ann White right now on the topic of like diagnostic design. It's about turbulence diagnostic. So it's not just the temperature profile or something. It's very tiny scale, like ion or electron gyrokinetic scale temperature fluctuation. So it's quite challenging.
I was just wondering, what was your motivation? If I'm correct, you did your undergraduate in Tsinghua University.
Okay.
And what was your motivation to enroll into the Fusion EP program in the first
Um, I was I was visiting institute in China, SWEEP, Southwest Institute of Physics in Chengdu. I don't know if you know that. So that is an institute for fusion research, plasma physics. And I happened to see a flyer about Fusion EP, and then I just apply it and I got it. That's a motivation. Very random, very casual. I didn't think about like apply for PhD directly because uh, I I'm not that I don't have a very strong motivation for a PhD at that time. So I think I would just go for master first. That's it.
Okay, great.
So shall we start? Oh,
Yeah, please.
okay. So today I'm going to talk on the topic prediction of high K electron temperature fluctuations in NSTX H-mode plasma. So anomalous transport caused by microinstability-driven turbulence is one of the biggest problems in fusion research. Turbulence-driven transport dramatically degrades the confinement in tokamaks. And we are specifically interested in one kind of device called spherical tokamak, in short ST, which is different from the conventional tokamaks in mainly four ways. ST has smaller aspect ratio, so it looks very compact. And ST has very high beta, usually an order higher than conventional tokamaks. And ST has high bootstrap fraction, which is favored by steady state operation. And ST has very better MHD stability because particles spend less time on the low field side region, which leads to the suppression of bad curvature instability. In terms of the connection to the research in our group, we are interested in ST because limited validation work has been done on ST, Meanwhile, there's more to learn about electron turbulent transport in ST, since in ST, electron turbulence dominates over ion and impurity transport. So turbulence transport is very complex. There's no simple theoretical model to directly explain the observations in experiments. The gyrokinetic model is the most reduced but sophisticated model for transport, turbulence transport that can be implemented in computers. However, it's not fully validated. Uh, so validation refers to the comparison between numerical simulation and experimental measurements of turbulent quantities such as density fluctuation, temperature fluctuation. And validation is very important because this is the only way we can gain confidence in predicting what's going on in a new device or new physics regime. So what we want to do is to eventually develop a high K temperature fluctuation diagnostic, since it has not been developed yet. So here, let me clarify what is high K. The K here refers to the physical wave number, K perp. So if K perp timing rho s is more than 1, then we call it low K. If otherwise it's greater than 1, we call it high K. The diagnostic available for turbulence study up to date are low K density fluctuation using beam emission spectroscopy, high K density fluctuation using coherent Thomson scattering, and low K temperature fluctuation using correlation electron cyclometry emission, but high K temperature fluctuation is unfortunately missing. High K fluctuations are critical for studying ETG-driven turbulence. And ETG is a kind of a drift wave type turbulence driven by the electron temperature gradient. So ETG turbulence is predicted to play an important role in determining the electron thermal transport both in theory and simulation. And high K temperature fluctuation in fusion plasmas are associated with electron temperature gradient driven turbulence, which can be seen from this figure. These fluctuations, if you calculate the wave number, these are high K fluctuations. And you can see the fluctuations are elongated in R direction. And this is actually called streamer, which is a sign of ETG turbulence. And so we are right now at a diagnosis design stage, and we want to incorporate the synthetic diagnostic into the design work. Synthetic diagnostics are computation models which translate the plasma quantities into the experimental measure quantities, or you can it can be understood as a filter. The field function is usually expressed like this, delta x, blah, blah, blah. And psi is called the point spread function, or it's just a weighting function, which is different for different diagnostics. So to generate the synthetic diagnosis, we need numerical simulations. So what type of simulation? Okay, we need nonlinear gyrokinetic simulation. And what cases to use? For this, we will use the H-mode in NSTX with high K density fluctuations already detected, because this guarantees that because there's a correlation between density fluctuation and temperature fluctuation. So it guarantees the existence of temperature fluctuation. So NSTX is a spherical talk mark cited in PPPL, now NSTX U for upgrade. Here lists some key parameters of NSTX. The aspect ratio is 1.25, very small. And take two different cases from the same shot at different times. Strong ETG case has relatively large current and smoother temperature and density profile. The physical parameters are all listed here. It's worthwhile to notice that these two cases are very highly collisional. We can see the new EI is about 1.3, 1.0, so it's very high collisionality. So we have two codes, gyro and CGYRO, both developed by General Atomics in California, San Diego. And gyro was used to run for these two cases by another student, Huan Hui, from PSFC, but not for CGYRO. So we plan to use CGYRO to reproduce the results obtained by gyro, because CGYRO has a more advanced collision operator. It's called Su-gamma model. While in gyro, the collision operator is just a very simple Lorentz pitch angle scattering model. So from this slide, we will show the results obtained with CGYRO and the comparison with gyro. So it's kind of like a benchmark work for CGYRO. And to make sure the CGYRO results are reasonable, it's very important for our further study. So this is a comparison of linear results between gyro and CGYRO with two collision models. The patch area is the response with the electron temperature gradient varies with within 90% and 110% of the experimental value. Gyro, the green curves are the references. The real frequency and growth rate are scanned from very low K to very high K, up to 60. For strong ETG case, CGYRO will produce the gyro result very well. Su-gamma predicts the growth rate to be lower, implying that the impact of the collision models. So we did the same thing for weak ETG case. So CGYRO Lorentz, there are different collision models in CGYRO, and CGYRO Lorentz basically has no difference from gyro Lorentz, except at very high K. This shows the difference in other aspects than collision model itself. For example, the implementation of the collision model or something else, I don't know. But anyway, the difference is not that crazy. However, for CGYRO Su-gamma, something crazy happened. At high K, I've encountered a convergence problem. So it didn't give me any reasonable values of omega and gamma. So this is probably due to the negative growth rate, as we can see from the tendency, the black curve on the right side. But gyro and CGYRO are both initial value codes, and they assume the growth rate to be positive. So if we get negative growth rates, the result is very likely not trustworthy. Now let's have a look at the nonlinear results. So the difference between linear and nonlinear is the linear is run at a single k, but nonlinear has different k's at the same time. So that means the interaction between different modes will be taken into consideration in nonlinear case. To obtain the integrated quantities like energy flux, particle flux, nonlinear simulations should be run. Here we put several outputs showing the simulation is done successfully. This is for the strong ETG case run with the Xiang model and experimental electron temperature gradient. So we can see that both energy flux and potential fluctuation get saturated when time goes by. And the spectrum shows the peak of the energy flux happens at k around 10, not exact, but close to the prediction of linear growth rate curve. And the same thing is done for weak ETG case. We did it with Xiang model, but like 40% higher electron temperature gradient, because at experimental value, the turbulence is suppressed. Then we calculated the saturated electron thermal power and made a comparison with gyro. For strong ETG, very good agreement is reached. While for weak ETG, the discrepancy is relatively large. But we noticed that the scale for the two cases are different. We can say the absolute discrepancy for weak ETG is not necessarily bigger than strong ETG. The important thing is using different collision model does give a relative different does give a relatively different but still consistent result. So this gives us the confidence to do further study with CGYRO. So once we are familiar with running CGYRO, the next thing we need to do is about the diagnostic techniques. So first, we will look at all possible techniques for high K fluctuation measurement. Potential candidates are soft X-ray, Thomson scattering, and electron cyclotron emission. Right now, I'm doing background reading on these techniques and learning about the pros and cons of them. Later on, I will determine one technique to implement the synthetic diagnostics. Then I will calculate the diagnostic, the sensitivity level and the signal to noise ratio to assess whether this is a good diagnosis, or not. If it's not, we have to switch to another technique. These three are the principles of these three techniques. So I will just skip them because you can find them on the textbook, like principles of plasma diagnostics. Here presents a summary comparison of the three diagnostic techniques mentioned just now. One of the most important things for diagnostic is the resolution, both spatial and temporal. The third column is a better resolutions achieved up to date, and the fourth column is a target resolution required for high K temperature fluctuation measurement. So a short summary. A high K temperature fluctuation diagnostic, which could be critical, but validation work of gyrokinetic models has not been developed yet. What I am doing is to assess the feasibility of high K temperature fluctuation measurement using synthetic diagnostics. And linear and nonlinear benchmark for the experimental cases are done with CGYRO, and good agreement with gyro are obtained, which means we are running CGYRO correctly, and we are ready to implement the synthetic diagnosis once the work with diagnostic side is done. Okay, that's all. Thank you for your attention.
Thank you very much for your presentation. It's such a complicated topic, and you made it very clear.
Sorry, I didn't phrase it well. If it's too complicated, you think.
No, it's a very interesting topic, and I'm glad to learn more about this field. So now we have time for questions.
Mm-hmm.
Okay, great. Thank you, Xiang, for this introduction to your work. It's not easy to compress so much. No. It was. Sorry. It was very clear. I could have used a little more time on each slides to get familiar with each of the ideas, but all in all, it was very clear and very interesting. So I was wondering, so you say there's high K temperature fluctuations. So sort of the first item of your summary could be important. It hasn't been developed yet. Yet you, if I understand correctly, you're reviewing existing diagnostics that could be used for this. Does that mean you will eventually propose some upgrades or improvements to those diagnostics to reach the resolution that you need, or do you think that they have just not been used yet for what you want to study, the fluctuations, the size of the fluctuations you want to study?
Okay, thank you for the comments, and it's a very good question. Thank you, Alex. So for temperature measurement, the techniques for temperature measurement is limited. You can only measure the temperature from the radiation, from the plasma, or you you use the laser or any beams. So first of all, the point I want to make is the techniques are limited. Just these 3 or 4 techniques. We have no other choices. So the difficulty with high K temperature fluctuation is, the resolution, both spatial resolution and temporal resolution. For high K temperature fluctuation, the spatial resolution required is less than 1 millimeter, and temporal resolution or the frequency resolution should be like up to megahertz. So it's quite high. So what we want to do is to first learn about the improvement or the advancements in all these techniques, and like what is the best achieved resolutions. So this summary is actually out of date. It's like 3 years ago, and it's copied from my supervisor's proposal. So maybe in 3 years there are a lot of improvement in the resolution. So I will need to learn about this from like talking to some experts in X-ray or these other diagnostics, or like just search for the relative papers. So we do need to know the best techniques, technology so far. This is one point. And second, if let's say if we found, for example, I'm looking at X-ray imaging right now, and we actually found that the temporal resolution can be megahertz. But that's for the emissivity. It's a different concept from temperature. If if you want to resolve the temperature from the emissivity, you also need to resolve the energy. So that will be another problem because if you want to resolve the energy, it will decrease the temporal resolution. It's a trade-off. So okay, the point I want to make is we want to find maybe a smart way or something like maybe we can sacrifice some resolution, maybe sacrifice the spatial resolution to get a higher temporal resolution, because we don't need a diagnostic that can resolve very, very well in both space and time. We right now, the goal of our project is to just develop maybe just to get to know one aspect of the temperature fluctuation, maybe just like the fluctuation level, and that will be simpler than the full fluctuation diagnostic.
Okay.
Sorry, is that clear?
Yeah, absolutely. So you say you're using synthetic diagnostics to sort of test the signal to noise ratio and other parameters of the diagnostic before to propose it as a candidate for electron scale fluctuation studies. I think another way to, or I think I've heard that another way to go about with synthetic diagnostic is to try to use existing signals from multiple diagnostics and try to make a
prediction, maybe neural network or something.
Prediction based on multiple inputs. Is that also within your considerations or not at all?
That's another aspect, I think. So what you are saying is to use, data from multiple diagnostic, right?
Yeah.
And to generate maybe more trustworthy or more accurate result. But if, let's say, if you have diagnostics about just temperature profile, you still won't get the data about fluctuation. I mean, from those diagnostics, you can get a better result for the temperature profile, but there's no information hidden in this data. So I know what you mean. For example, I think like neural network techniques can be used to generate like a better prediction of this temperature profile. But what we want to do is more from the physics side. It's not about signal or data processing.
Okay.
Okay.
So basically, you're saying it wouldn't help to get like good spatial resolution without necessarily. It wouldn't help your trade-offs to combine the outputs of several diagnoses.
Not necessary. It could help. For example, I saw a paper about like so you have Thomson scattering, Thomson scattering diagnosis about the temperature profile at a very, very, very different. No. Very, very close time. I mean the neighboring distance between the two measurements is very maybe milliseconds or more than 10 milliseconds. So on that paper, they use the neural network. They combine the diagnostic of Thomson scattering and scattering, diagnostic from the X-ray to improve the temporal resolution, because they have the diagnostic that is more dense in time.
Mm-hmm.
So they have the data from soft X-ray, and they have the data from Thomson scattering at some more different times. So in that way, you can improve the temporal resolution, but yeah, the problem with that is it's still not enough for the temperature fluctuation.
Okay. Okay. Thanks.
Thank you.
Thanks, Chen, for your talk. I have like one question on like what's the simulation domain that you used for the simulation? Is it like you just simulated one radial flux surface and then it's
so the simulation is done locally. It's done at a specific magnetic flux surface.
okay, and it's global in the polar direction.
It's not global. So there are I don't know if I have a good picture for it. So the simulation domain, like this, for example, this figure, x is the radius centered at that flux surface, and y is the poidal direction. So the unit you can see is several rho s. Rho s is an ion sound gyro radius. Is very small.
Okay, so y indicates polarity, but it's just basically a different field lines, or it's the same field line which is just repeatedly extended over all the flux surface.
It's the same. We assume it to be on the same flux surface.
Okay, yeah. Okay, so yeah, okay, thanks. And like I have one question regarding the synthetic diagnostic, because like we have the distribution function from the gyrokinetic equation. So if we take the moments of this distribution function, so we can actually find the temperature. Like in turn, we can find the temperature fluctuations if we consider, like if we split the distribution function and then like an equilibrium part and a perturbed part, which perturbed part corresponds to the temperature fluctuations. So how is it done in your case?
Sorry, I don't answer your question. Could you say it again?
Yeah. So like we have this distribution function.
Distribution function.
Yeah, in the gyrokinetic equation.
Which slide?
Like the gyro, maybe you can go to the like in the first few slides, it will be there. Yeah, like when you talk about the 6D to 5D.
16.
No, sorry. Like in the third slide.
Third. This one?
Okay, no, sorry, the fourth slide. Yeah.
This one?
Okay, so here, yeah, exactly. Okay. So here you're going from a 6D to 5D, which means you're going from a kinetic equation to a gyrokinetic equation? Like,
so gyrokinetic model or gyrokinetic equation is a reduced model from kinetic equation, right?
Yeah.
So yeah, we average the faster gyro motion of electrons and ions, so that it's 60, because the distribution is a 60 is a function in 60 phase space, right? X and V both have 3 dimensions. So by averaging the faster gyro motion, it could be reduced to 5D, and it can be implemented in computers.
Yeah, so this 5D equation has distribution function in it.
Yeah.
So you avoid the distribution function in time.
Yes.
So
yeah.
Since you have the distribution function in time, so you can actually find the temperature by just taking the moments of this distribution function.
Yeah, sure. What you are saying is actually so you want to reduce this gyrokinetic equation to like more reduced fluid equations, right?
Not exactly like that. It's okay. So you like this code actually solves for it starts with some distribution function.
Yeah, you are solving the distribution functions.
Exactly. Right? So the solution is f. So you know f in different moments in time and space.
Yes.
So if you find the moments of this distribution function, you can find the t
you
in
can find the temperature fluctuation from this code.
Exactly. So what's the use for the synthetic diagnostic in this case?
Okay, the synthetic diagnostic is perhaps I have a better sorry. So so from the simulation we have the output the raw data, we call it. So the synthetic diagnostic is a computation model, as I say. So it's actually a filter. So after this filter, the filtered data, we call it a synthetic signal. And this signal can be directly compared to the experimental measurement. So we're not comparing experiment measurements with raw data. It has to be processed.
Okay, so the raw data means the temperature fluctuations here. Yes. From taking the moments of the distribution function.
Yes.
Okay.
Because the measurement you have to take into consideration like the filling geometry, like a lot of things, like the detector, the filter, I mean the hardware filter. So what you measure is not just the pure fluctuation, temperature fluctuation.
Okay. Okay, so it's okay. It's okay. Yeah, now I can understand. Yeah, and I have one more question. Like, so you say like you need the high K fluctuations. So can you tell about the resolution that you use for the Y in the Y direction? Like, what's the grid size?
Sorry. Could you repeat again?
Yeah, so what's the resolution that you use for in the Y direction to resolve this high K? high K modes?
For high K in y direction or parietal direction, we need resolution up to like millimeter. For X, maybe it's lower.
Ah, okay, okay. Yeah, thanks. Thanks, Chen.
Hello. Well, the first thing, I was so happy to hear that you also study Nancy. I'm a first year student also with Yusun, which is here also. And yeah, I'm so happy for you that you end up in MIT, MIT doing such an interesting research. In my case, I think I have more simple questions than the previous ones.
Yeah.
If I understood correctly, you talk about the spherical tokamak that could be operated steadily.
Steady state. Where?
Steady operation of the spherical tokamak.
Yeah, because it has higher bootstrap fraction.
Okay, so how can it be operated steadily? It doesn't use the transformer effect to induce the current anymore?
I don't know so much about that.
Okay.
But yeah. what I know, yeah, is just very simple. Higher, so bootstrap current is self-generative current. So you don't need external current drive for the tokamak.
Okay. Okay. And another question is that you found that the high temperature one was missing. You have low density, high density, low temperature, and high temperature was missing. I'm not sure if you already said, but what could be the final application of finding this thing? Could be only useful for spherical tokamak, or could be used also for another designs?
So these diagnostics, some are installed on conventional tokamaks, some are on spherical tokamaks. For example, Thom's high K density fluctuations. On NSTX, we have coherent Thomson scattering system that can measure high K density fluctuation.
And there is a need of high temperature fluctuation in the field right now.
Yeah, we need it because the most important thing, like for plasma transport, is the validation of the gyrokinetic model. So we're believing that gyrokinetic model is sophisticated enough. So we don't have like any missing physics. Okay. So it's fundamentally correct, but gyrokinetic model cannot, the prediction from the simulation cannot match the experimental yet in some way. So actually, we need more data from experiment to support our this validation work. And these three diagnostics, they provide limited information experimentally. So this high K will provide additional or probably more important information about turbulence. And it's a high K, so it's more related to electron transport. And electron transport is like in spherical tokamak, it's dominant. It's dominant over ion or other impurity transport. So this is very important.
Okay. Yeah, thank you very much.
So in a sense, your ultimate goal is to explore the limits of the gyrokinetic model.
You can
or
say
this
that
limit.
we want to make prediction based on the gyrokinetic model, but right now we are not confident enough, right? If we want to like predict what is going on in ether, it's the plasma parameters are all new, so we don't know whether the prediction is correct or not. So our goal is to gain the confidence in this model, and to do that, we do need to have more experimental data to compare with the simulation and to know the deficit. Maybe there are some missing physics, like in the collision or some other things. We do need to, if there's some errors or mistakes, we do need to make them up. So.
And if I can comment, if Danielle is still here, if I can quickly comment on your first question. In my understanding, the spherical tokamak is exactly the same working principle as the regular tokamak. You just have a smaller R0, so the aspect ratio goes down.
Mm-hmm.
And so it results in the confinement improvement and the higher bootstrap fraction that Xiang was mentioning in his presentation. But it adds some complication in the fact that the central column has to be sort of less, there's less space for shielding in the middle. So the complication is you get sort of higher particle fluxes on that critical part of the device, and then it's not clear if you're going to be able to go to high powers with those devices. And then devices like MAST upgrade or like NSTX upgrade are trying to see if you can make it, among other things that they're exploring, of course, trying to see if it's technologically viable for a reactor.
Mm-hmm.
I was just very surprised about the steady operation of a tokamak.
Yeah,
Steady state operation.
Okay.
It's certainly more favorable for steady state operations, but then there's that trade-off, right, on the how much heat and particle flux in the material set, especially the magnets.
Mm-hmm. Okay, thank you.
Okay, thanks.
Any more questions?
I want to ask maybe a very basic question. You mentioned about high K temperature fluctuation, and then you mentioned maybe you can make some trade-off between temporal resolution and the spatial resolution. So
Mm-hmm.
what is the minima temperature resolution or spatial resolution you need to diagonal high K temperature fluctuation?
I don't know this yet. Yeah, I'm right now trying to figure it out. So the resolution for the diagnostic is a big problem. So I can talk a little more about X-ray imaging, which I'm looking at. So as I say, the best temporal resolution for X-ray imaging or yeah, emission is about 1 megahertz. Is this enough? Maybe it's not, because yeah, in the high K temperature fluctuation is centered actually to be like 1 or 2 megahertz. So according to the sampling theorem, you need twice higher sampling rate than that. So 1 megahertz per ray is still not enough for that. Yeah, this is one thing. From about the spatial resolution, it's limited by the aperture of the detector. So if we can make it smaller, then we will get a higher, and we arrange a lot of chords, then we can get a higher spatial resolution. So these all involve very these are all very engineering.
Yeah.
So actually, I still don't know the answer yet. But soft X-ray is line integrated. So what I'm doing is to look at the line integrated signal. I want to find out whether the line integrated signal can reflect some information about the local temperature fluctuation. So if like, let's say if we can, if the line integrated information is 1-to-1, can be 1-to-1 mapping to the local information about the temperature or temperature fluctuation, then we just line integrated signal measurement or is enough. And for line integrated measurement, we have it's easier to detect. I mean, we can get a higher spatial or temporal resolution.
I see. Thank you.
Thanks.
Any other questions? Last chance. Well, if no further comments or questions, I would like to thank all the participants, and I wish you all the best with your work. And this talk will be available on YouTube soon. And I hope to see more questions and comments on the topic there. I wish you a nice evening and happy holidays in the US.
Thank you all, guys. Thank you for the.
Thank you very much, Xiang.
Give a talk. Thank you.
Happy Thanksgiving.
Thank you very much.
Bye.
Bye.
Thanks, Chen, for your talk.
Thank you. Okay.
Okay. Thanks again. That was really nice topic. Interesting, very new to me.
Thanks. I find I'm not handling the question very well. So Alex, you ask a very good questions actually. I like those questions.
I thought it was a very general question, but so are you in touch with Luis Delgado Aparicio in Princeton?
Actually, I wrote him an email, but he didn't reply. You know him?
I met him during my summer internship, and he was at some point trying to recruit me to work on X-ray diagnostics.
Yeah.
And I saw him again when we were in Kadahash. He was installing his sort of new optimized X-ray imaging system on West.
Yes. Yeah. He has
He was very much looking for students and collaborations.
Okay, that's good to know. But yeah, I wrote him an email and waiting for his response, but he didn't. It's kind of frustrating to me.
There is another person who's very nice. He's an sort of older researcher, so I think he also has more time. His name is Manfred Bitter.
Man, could you spell it?
Yeah, I'll write it down in the chat. So they work closely together, and maybe Manfred will help you get to Luis. Bitter.
Okay, I will check it. Oh, Peter. Okay, Manfred. Okay, thank you. I will yeah, try to get in touch with him.
They seem to be very much at the state of the art in soft X-rays, or so they advertised.
Right. Yeah, you're right. Louis, they are developing I don't know whether it's new or not. It's not that new, maybe called optical soft X-ray, maybe imaging or something. So it's energy resolved. So in that way, you can infer the temperature from the emissivity measurement. Because yeah, the emissivity is proportional to the factor of h nu by T. I think you know it, the principle of soft X-ray.
I might have seen it, but I don't have it on the tip of my head.
Yeah, I can show you. I have.
But you don't go to it through you don't go through Stefan Boltzmann. It's something different, right?
Here. Soft X-ray. So soft X-ray is the brainstorm and recommendation continuum.
Yeah.
And also some line emission. But the most important thing is the brainstorm emissivity. No, the continuum. The continuum part of the emissivity is proportional to this factor. So there's TE here, right?
I actually don't see your screen. I see the screen, but I see the presentation. I don't see the.
Can you see it?
Yeah, now I see the.
Here. So you can infer the TE from the P or brightness or whatever emissivity measurement.
Okay.
So that's what I want, I think. So I do want to know from him that's what is the best resolution they achieved.
I actually have a few presentations that he had sent me that summer. If you're, I mean, you probably have more information than I, but if it's of any help to you, I can forward them.
Okay, yeah, that's good. Thank you.
Yeah, it seemed to be an extremely versatile diagnostic. Like in his presentation, he seemed to be able to access so many plasma parameters. It was very impressive.
Yeah, thank you. It's I think yeah, there are a lot of things to explain in the presentation. Some basic concepts. So I'm feeling like that. In the first part of the presentation, I I'm just not touching the motivation of the project. So it's until like slide 5 or 6, I mentioned the high K temperature fluctuation.
No, but you know, it was, I think it was a very good start because as you noticed, there were a few people who are in their first master year. So they, I mean, unless they did something during their undergrad, they probably have very little ideas about fusion at this point, and about the different fields of specialization. So I think it's excellent to, you know, give some general pointers on, on the context, of this study. And no, I think presentation wise, it's really excellent.
Now I'm trying to converting it to the student seminar next week.
Oh, is it your turn?
Yeah. Oh, I hear that.
Well, you got some drill today. That's.
Oh.
I guess it's a good rehearsal.
Well, yeah. That was my idea. I thought, it's a good rehearsal.
I mean, this is also kind of the point of these talks, I think, like, we're not expecting people to make a new presentation only for this, but more to sort of either recycle something they've already used and adapt it a little bit to the sort of master level, or to, use it as a preparation for another presentation.
Yeah, sure. Yeah.
Well,
So
good luck next week.
Yeah, I'm still editing the new presentation because some people are from non-fusion community.
Oh,
so,
yeah,
like,
that's different.
They don't know, they know nothing about plasma. So like drift, what is drift? So I need to explain those. I need to add more things.
But those student seminars at MIT are actually really nice and super interesting, also because they encourage people to criticize each other's presentation. I think it's very valuable a very valuable exercise for the speaker in the end. It's a course. It's mandatory for us to take it. For it, when you are from the third year on. The first 2 years you don't need to do it because you focus on the courses and you don't have so much time. So from the third year on, it becomes a course and it has a lot of credits. You have to. Yeah, I saw also that Professor Hutchinson tends to grill students a lot. So he's a chair. Yeah, he will always be present and ask questions or comments. So yeah, you cannot get rid of him. Well, I'll make sure that I'll be there to support you next week. Oh, thank you. I hope, I will practice more. I think, I think I'm not really good at handling questions. Sometimes, sometimes I just don't know the answer. Sometimes even I know I cannot express it very correctly. I need some time to think about how to think about the expression, the correct expression in English. Oh, it's not easy. Well, I think that's the same for all of us.
Yeah, it's absolutely
non-native
fine.
Speakers.
I think you are better than me. We have the easy side today also, right? We're on the public side, so we can ask very general and make up very approximative sentences, and then it's to the speaker to sort of figure out what we actually meant. And how to say, you were asking questions about the diagnostics. Well, I'm not that familiar with all the diagnosis, so I'm doing reading on those things. So when yeah, if you ask questions about the diagnostics, I will be maybe just stuck there.
Well,
Yeah.
I gotta get back to
Yeah.
my girlfriend and and girlfriend's family. We're soon leaving soon for Thanksgiving dinner, so
Cool.
Have a nice time.
Yeah.
Okay.
it was great seeing you guys and
Nice to meet you guys.
See
get
you.
your presentation.
Yeah, thank you.
Bye.
Have a good night, Akina.